Hello, y'all. Welcome to lesson 78 of my DP chemistry curriculum. Today we're going over reactivity 1.4.2 and 3, part of the HL curriculum. Reactivity 1.4.2 talks about changes in Gibbs energy, which is delta G, which relates the energy that can be obtained from a chemical reaction to change in enthalpy. Delta H, change in entropy, delta S, and absolute temperature T. So basically, how does Gibbs energy change with enthalpy, entropy at a temperature? We're going to be using this equation. Delta G equals delta H minus T delta S to calculate unknown values of these terms. As long as we have any three of these four terms, 1, 2, 3, 4, we should be able to calculate the others. Further use that we must know is delta H and delta G are kilojoules per mole, and delta S is joules per Kelvin per mole. Furthermore, in reactivity 1.4.3, we're going to talk about how at constant pressure, a change is spontaneous in Gibbs energy, delta G, if it is negative. So spontaneous reactions happen at negative delta G. So we'll be able to interpret the sign of delta G from thermodynamic data and determine the temperature at which a reaction becomes spontaneous. So with that said, let's begin by talking about what is spontaneity or a spontaneous reaction. So you know these, they appear in nature all the time, but this is something that occurs without the addition of energy. And when we say that, we're saying except activation energy. So for example, when you start a fire, it will continue to burn on its own, but if you start cooking food, unless you continuously apply heat, it won't cook. So the fire is spontaneous while the food is non-spontaneous. You must continue to add heat to cook something, not spontaneous. A fire will spread spontaneous. So we often um, use the analogy, it's like a ball rolling down a hill. It will continue rolling. So ball will roll till it reaches the bottom. And that's very much like a spontaneous reaction. It will go until there are no more reactants. So we're not really reactants. We're not really thinking about equilibrium too much. We will eventually bring equilibrium into this, but not right now. It's just going to continue going down. Sometimes it needs an initial push at the top. That would maybe be the activation energy. But once it's going, it's going. That's spontaneity. Now, we can apply this in the addition of things like entropy. So the second law of thermodynamics says that entropy increases or tends to increase. And so when we look at changes in entropy in a reaction, so we look at the change in entropy total, we know that if something's spontaneous, we generally have more entropy at the end because that would mean the particles have dispersed, doing what they want to do, what is kind of spontaneous. So if we look at the total entropy of a system, or the total entropy period, we generally look at the change in entropy of the system plus the change in entropy of the surroundings. So how does this relate to spontaneity? And we say that is going to be greater than zero. The entropy change is going to be greater than or at least equal to zero because we know entropy is tending to increase. That is that law. So when we look at a spontaneous reaction, some reactions may have a decrease in entropy, but are still spontaneous. And that's usually due to the other thing. Spontaneous. What other thing am I talking about? I'm talking about the entropy of the surroundings. So fire, generally, like your reactants can oftentimes become ash, and you do get some that are gas. So maybe instead we look at, we take a dissolved solid, so like Na aqueous plus Cl aqueous, and these are ions. and over time they will become NaCl because all the water will evaporate solid. And that is a spontaneous reaction. Water will naturally evaporate, bringing these back together. The reason this is still spontaneous is because the in surroundings, entropy in the surroundings greatly increases. And that's where we get this value right here. So even though this reaction, the entropy of the system is negative, the entropy of the surroundings greatly increases as all those water particles go from liquid to gas. So we can still have spontaneous reactions that still follow the second law of thermodynamics, saying that entropy will increase. So where does this all point to? Well, this points to actually using entropy to figure out, is a reaction spontaneous? So let's use entropy to determine spontaneity. Spontaneity. I probably spelled that wrong. Give it your best shot. So how do we do that? We do that with Gibbs energy. So what the heck is Gibbs energy anyways? Well, very specifically, Gibbs energy is the energy associated uh, with a chemical reaction, both in respect to in respect to entropy change from the reaction and entropy change in the surroundings due to transfer of heat. It's a very long definition, but basically saying that we use Gibbs energy to determine the spontaneity of a reaction by looking at the energy associated with both the chemical reaction itself as well as any endo or exothermic changes in the reaction. So any heat associated with the system and surroundings. So it takes into account both the release or absorption of heat, delta H, as well as the actual change in entropy of the system itself. It combines enthalpy and entropy together in one case. So how do we actually determine it? Well, let's start with delta S of the surroundings. What the heck is delta S of the surroundings? Well, the entropy change of the surroundings is a function of the enthalpy divided by the temperature, and you'll notice a negative sign. That's just because, oh, double tapped. You'll notice a negative sign, and that is due to the fact that if we release heat, the entropy goes up. If we absorb heat, the entropy goes down. So it must be inverse from system because the heat going into the system is coming out of the surroundings and vice versa. So we now have our entropy of the surroundings. We can include that with the entropy of our system, and we can transform the equation. And when we do that, we get delta G standard, so the standard change of Gibbs energy is equal to delta H standard minus T times delta S standard. A couple things of note, Gibbs is in kilojoules per mole. Delta H is in kilojoules per mole, but delta S, T is in Kelvin, and delta S is going to be in joules per Kelvin per mole. So you have to rectify the fact that this is in kilojoules and that's in joules. So whenever you do calculations, you're going to have to divide by 1,000 for your entropy values. So from this, we can determine that delta G depends on the sine of delta H, the sine of delta S, and the absolute temperature. So what do we actually mean by that? Well, first, let's just put it into practice. Let's do an example. If we have a reaction where delta H is equal to 178 kilojoules mole inverse, delta S is equal to 161 joules Kelvin inverse mole inverse, and the absolute temperature is 298 Kelvin. Well, we can just plug these values in. This is how you use delta G. And delta G is just going to be equal to 178 minus 298 times 0.161, remembering we have to divide by 1,000 to turn it into kilojoules. And you'll find that the delta G is 130 kilojoules per mole. Now, this is important because it tells us that this reaction must absorb energy. If it must absorb energy overall, take energy from the surroundings, take energy overall, we know that it is, while it is increasing entropy with the positive delta S, the amount of heat it takes in as an endothermic reaction is too much. So this is likely going to be a non-spontaneous reaction. When we look at the sign of delta G, if delta G is negative, then it will be spontaneous. The reaction will just occur. If delta G is positive, it is non-spontaneous. And if delta G is just flat out zero, we know our reaction is at equilibrium. It will not move forwards or backwards, or rather, it is moving forwards and backwards at the exact same rate. So, the last part of this is we can therefore determine spontaneity. Spontaneity, I think that might be an E, from signs of delta H, delta S, and T, well, at least the magnitude of T. So what do I mean? Well, we go back to our equation. Delta G is equal to delta H minus T delta S. If our if our enthalpy is negative and our entropy is positive, regardless of what T is, this whole value, negative minus a positive number, will always be negative. This will always be spontaneous. Meanwhile, if we have a positive delta H minus T and a negative S, this will always be non-spontaneous. Positive minus a negative is always positive, therefore delta G is non-spontaneous. If we have a positive delta H minus T and a positive delta S, well then, it kind of depends on temperature. The higher temperature is, the larger in magnitude this number is, and therefore subtracts from our positive number. This would be spontaneous at high temperature. Lastly, we can look at a negative delta H minus T and a negative delta S. Again, we have a negative value, but if this value times this value is so much larger than our enthalpy, in that case, it would be non-spontaneous. So this would be non-spontaneous at a high temperature. The last thing we can do here before I end this video is we can look at our original reaction right here. So in our original reaction, we found that this reaction is non-spontaneous. However, we could find a temperature where it becomes spontaneous. So when delta G goes from its positive 130 to 0, we could find out where that reaction is spontaneous. I'm going to move these values, but I'm now going to leave temperature behind. So we'll say this is spontaneous at T equals question mark. And now we can plug it in. So we're going to say delta G equals 0. That will be the transfer point when it goes from positive to negative. And so now we can just plug in 0 equals 178 minus T, which will stay a variable, times 0.161. Therefore, T times 0.161 equals 178 with a little bit of moving around here. All we have to do is plug this value into our calculator. And when we do that, we solve for T and find that the temperature this becomes spontaneous at is 1,110, accounting for sig figs, Kelvin. So at any temperature greater, so at T is greater than 1,110 Kelvin, it becomes spontaneous. So by plugging 0 in for delta G, that transfer point where it goes from non-spontaneous to equilibrium to spontaneous, we can find that it becomes spontaneous at a temperature greater than about 1,110 Kelvin. So I hope this helps you understand Gibbs energy, spontaneity, and doing these calculations, and have a great